Various forms of energy. First, heat. We know that the frictional force is excluded from the category of conservative forces. However, work is associated with the force of friction. A block of mass small m sliding on a rough horizontal surface with speed v naught comes to a halt over a distance x naught. The work done by the force of kinetic friction small f over x naught is minus f into x naught by the work energy mv naught square upon 2 is equals to f into x naught. If we confine our scope to mechanics, we would say that the kinetic energy of the block is lost due to the frictional force. On examination of the block and the table, we would detect a slight increase in their temperatures. The work done by friction is not lost, but is transferred as heat energy. This raises the internal energy of the block and the table. In winter, in order to feel warm, we generate heat by vigorously rubbing our palms together. A quantitative idea of the transfer of heat energy is obtained by nothing that 1 kg of water releases about 42,000 joule of energy when it cools by 10 degrees Celsius. Second, chemical energy. Chemical energy, one of the greatest achievements of humankind, occurred when we discovered how to ignite and control fire. We learned to rub two flint stones together, mechanical energy, got them to heat up and to ignite a heap of dry leaves, chemical energy, which then provided sustained warmth. A matchstick ignites into a bright flame when struck against a specially prepared chemical surface. The lighted matchstick, when applied to a firecracker, result in a spectacular display of sound and light. Chemical energy arises from the fact that the molecules participating in the chemical reaction have different binding energies. A stable chemical compound has less energy than the separated parts. A chemical reaction is basically a rearrangement of atoms. If the total energy of the reactants is more than the products of the reaction, heat is released and the reaction is said to be an exothermic reaction. If the reverse is true, heat is absorbed and the reaction is endothermic. Coal consists of carbon and a kilogram of it, when burnt, releases 3 into 10 raised to power 7 joule of energy. Second, chemical energy. Chemical energy is associated with the forces that give the rise to the stability of substances. These forces bind atoms into molecules, molecules into polymeric chains, etc. The chemical energy arising from the combustion of coal, cooking gas, wood, and petroleum is indispensable to our daily existence. Third, electrical energy. The flow of electric current causes bulbs to glow, fans to rotate, and bells to ring. There are laws governing the attraction and repulsion of charges and currents. Energy is associated with an electric current. An urban Indian household consumes about 200 joule of energy per second on an average. Fourth, the equivalence of mass and energy. Till the end of the 19th century, physicists believed that in every physical and chemical process, an isolated system is conserved. Matter might change its phase, that is, glacial ice could melt into a gushing stream, but matter is neither created nor destroyed. Albert Einstein, 1879 to 1955, however, showed that mass and energy are equivalent and are related by the relation E is equals to mc square, where c is the speed of light. The value of speed of light is 3 into 10 raised to power 8 meter per second. Thus, a staggering amount of energy is associated with a mere kilogram of matter. E is equals to 1 into 3 into 10 raised to power 8 whole square joule, that is equals to 9 into 10 raised to power 16 joule. This is equivalent to the annual electrical output of a large 3000 megawatt power generating station. Fifth, nuclear energy. Most destructive weapons made by men, the fission and fusion bombs, are manifestation of the above equivalence of mass and energy. On the other hand, the explanation of the life-nourishing energy output of the sun is also based on the equation E is equals to mc square. In this case, effectively, 4 light hydrogen nuclei fuse to form a helium nucleus whose mass is less than the sum of the masses of the reactants. This mass difference, called the mass defect delta M, is the source of energy delta M into C square. In fission, a heavy nucleus like uranium U-235 is split by a neutron into lighter nuclei. Once again, the final mass is less than the initial mass, and the mass difference translates into energy, which can be tapped to provide electrical energy, as in nuclear power plants, controlled nuclear fission, or can be employed in making nuclear weapons, uncontrolled nuclear fission. Strictly, the energy delta E released in a chemical reaction can also be related to the mass defect delta M is equals to delta E upon C square. However, for a chemical reaction, this mass defect is much smaller than for a nuclear reaction.